This video is sponsored by Rewarded View. Are you tired of just scrolling through your phone without making any profit from it? Well, Rewarded View is for you. If you have an Android phone, then head over to rewarded-views.prima.ai, download the app, and start earning today. All you have to do is create your account, watch videos, and get paid for each and every video that you watch. So, what are you waiting for today? Download Rewarded Views and earn the smart way.
Hey guys, how are you doing? How's your day going? And this starting how was your night? Hope you had or are having an amazing and a beautiful day today. Welcome back to Python Everywhere. Everything Python. I forgot the name of the series. Firstly, so this is part two. In this series, we are going to be covering every single thing Python related, from data science to web to app development. Anything your mind can comprehend that it can be done with Python, we would do it. And in the last video, we just did a basic introduction to Python. Obviously, since this is more of a practical form of Python, dwelling on the basics and intro to Python, which is everywhere all over the internet, including on my YouTube channel, is not necessary. But if there's anything that you'd want me to retouch on, feel free to leave it in the comments. But without further ado, today's one is going to be a doozy. This is going to be a bit bulky. Sadly, this isn't, like I said, a detailed video. This is more of brushing up your memory if you're already introduced to it. But in the case of this topic, because this is quite a complex topic, I would advise you to first watch this, have a basic understanding of the concept. I'll try and explain and simplify the concept to you, the understanding of and every, like any beginner. So even if you are not a Python developer but you want to understand and become familiarized with this topic, you can watch this, and after which you can look for someone's video who now dives deeper into it. Because if you just hop out of it and just go and look for someone who is focusing on it, you might get a bit confused. This is more technical. There's a mathematical aspect to it which I wouldn't really be covering in this video. But yeah, don't forget to like, subscribe, share, leave a comment, ask any question you want to ask in the comment. And let's get into data. Sorry, no, sorry, data structure and algorithm. Yes, the big DSA, the DSA that everybody runs away from in Python. We are going to touch on that today. But before we go into that, let's understand what an algorithm is. Everybody on social media knows of their algorithm. Oh, the TikTok algorithm is not favoring me. Oh, I found a hack and I've cracked the YouTube algorithm. Oh, this is what the new changes to the Instagram algorithm is doing. Everyone is like algorithm, algorithm. I doubt there's anyone who has a phone that has not heard that name, algorithm, being applied. But what do you technically understand by that word algorithm? Well, an algorithm is a step-by-step set of instructions or rules designed to perform a specific task or solve a problem. So an algorithm can be create an algorithm to teach me on how to cook rice, an algorithm to help me add two numbers together, an algorithm to figure out what content would have a higher retention rate to said users. So some of the characteristics of an algorithm are an algorithm must be finite, finite. That is just the saying an algorithm must have a limited number of steps. You don't want to have like an infinite number of steps, because at the end of the day you want your program to come to an end. Which is why usually when you're running a loops, I didn't really touch much on loops in the last video, but I have videos where I've done that. When you're working with loops, you would always need to have a break statement. Your loops, you don't want an infinite loop. At the end of the day, whatever you're doing must come to an end. Nothing lasts forever. It must be unambiguous. That each step should be clear and straightforward. It should be concise. It shouldn't be using you to do tumbo, and it may have zero or more inputs. So the supervision for the algorithm, certain algorithms don't require input from users, whilst there are some algorithms that require input from users. But even though an algorithm may not require an input, an algorithm should always produce at least one output. And feasibility, an algorithm should be feasible and efficient in terms of time and resources. You are always trying to optimize whatever it is you're trying to do with that algorithm. Some sample algorithms, let's just say one finding the maximum number. So if we were to plan the algorithm for this, we would say, okay, let's create a variable called max, and with the first element of the list. So let's say we have a list of numbers already given to us. So with the first element of the list, you assign that very first element in the list that is at the index 0 to max. Now, as I'm saying this, I'm speaking English right now. So anybody with any technical background, whether you're a Java, JavaScript, Python, whatever, C plus, you'll be able to implement this. So you now say, okay, iterate over each element in the list. That's just going through each and every element in the list from index 0, go to index 1, go to index 2, go to index 3. If the current element is greater than max, that is greater than the current value saved in. So let's say we have a list, for example, we'll do this in Python shortly. We have a list, let's say 5, 10, 15. You initialize the max variable and assign 5 to it because that is first element in your list. You now iterate of it. So the next element in the list is 10. Is 10 greater than 5? Yes, it is. Now assign 10 to 5, 10 to max. Sorry, so now max is going to be equals to 10 instead of equals to 5. And you continue doing this until you reach the last element in your list, and then you return max. So now if we're doing this in Python, so you can do this without a function. But like I said, we try to promote modular programming in Python. So they call it a Pythonic code. Functions technically is not a Pythonic feature, but we're going to be using functions to do this. So say def, which if you remember from my last video is how you define a function. I'll just give function a name, find underscore max, and we'll have our parentheses. So we want to accept a list, and this list is going to be numbers. It can be whatever you want it to be. The word is your oyster. Don't forget your column. We're going to indent it because Python rules on indentation. So the first thing we're going to do is assign the first element. So we're going to assume that the user is going to give us a list. So once we get the very first element of that list and assign it to the max element, this that we should create. So let's say max underscore numbers, max number. I'm going to say because so numbers is the elements, but we don't want to assign the whole list. We want to just get the first index. Remember how to fetch a value from a list. Use the square brace and the index of which you want to fetch. We did all this in the last video, and now we're going to look through it. So I think we touched on this in the last video, but if we didn't, like I said, I have a video where I did this. So we're going to say for num in numbers, we're now going to say if num is greater than what is currently in the max value. So greater than in Python is just the greater than sign. Max underscore number. We're going to have our column. So for is a loop if it's a conditional. We're not going to say reassign the new value. Max underscore number is now going to be equals to no. And this is going to repeat and repeat and repeat and repeat until no new reassign until we reach the ending of the list. And after we do this, remember I said if you want to return the value so you can reuse it, you do return, and you're going to return the max number. Very simple. Now we're going to now assign it. So just say um find underscore max. Let's just pass our list here. Just say 2, 4, 6, 8, 10. And if we run it, let's print it. Let's print it. It's going to return 10 because 10 is the maximum. Now, this is obviously if you're actually writing a program where you would need to do this, you're obviously not going to do this because someone has created this code already and saved them into a model file, which we are going to touch. I think on PyCharm it allows you to see all the models, right? Hmm. I don't even know what file this one will be saved in, and I'm just thinking, wait, let's check M. I'm looking for the max function. Is it going to be under max? Yeah, let's not stress ourselves. Just know that someone on their own has gone through the trouble, gone through the stress of doing this for you. And now instead of you having to now do find marks and all these things and redefine it yourself, all you have to do is just call the max function. We need to import it. Call the max function and run it. Yeah. So Models, we're going to touch on models in our next video. But yeah, this max match I just called was imported from a model. Okay, what else I'm touching next? Okay, now so what are some of the qualities of a good algorithm? A good algorithm must be correct. For example, had it been I had run this code now and it returned 6, that is inaccurate. And if let's say on my own I don't go and now check through this, it's going to cause a lot of issues down the line in my program. So whenever you're creating an algorithm, you must cross check and make sure that algorithm is correct. It must be efficient. So there are always there's always going to be different ways to attack a problem. But you'll be looking at which one is going to cost the less, which one is going to save the most time. This is when you now start coming across things like the big annotations, which I'll brief through shortly in the next video. If you want me to do a full video on that, let me know. It must be simplified and it must be clear, it must be understandable, it should be scalable. So that means now I'm using a list with like 5 elements. If I decide to add a list with 1,000 elements, it should be able to handle that, and it must be robust also. So now that I've understood what an algorithm means, let's understand what data structure is. A data structure is a way of organizing or storing data to enable efficient access and modification. So it's just, for example, list. Instead of having two in one separate location, four in a separate location, you combine all this together and have them stored in a structure, in a data structure. So the importance is there's is essential for effective data management and retrieval. Take for example, in a school, let's say back then when everything was done analogly, manually, you have files for all the students. Had it been they were just had all the files scattered everywhere, if let's say a student comes down, it's going to be an issue if you want to find that student's file. But if you arrange, okay, these are all the students in JS1, these are all the students in SS2, when someone comes to ask them, okay, what class are you in, they'll tell you what class are you, now go and find, okay, this is where all the files for students in this class are stored. So it makes everything organized. It's an efficient way to run or handle anything, and it also helps to optimize your algorithm performance. Because, for example, like I say, if 2, 4, 6, 8, and 10 were all over the place, before we finish retrieving it, then now implementing to our function will be a whole different story. If you count the amount of time that it's going to take, it would be higher. So now types of data structures, there are two main types, the linear data structure and the non-linear data structure. I don't think you need any definition for that. For linear data structure, the elements from a sequence and each element has a unique successor. That is like, for example, now here you have two. Immediately after two, you know it's four. It's forming a straight line and each of them are following after each other. Four follows after two, six follows after four. An example is an array. An array is a collection of elements and that is identified by an index. And in a case like if you're working with other languages, a list is an array. So Python list is an array. So no other further explanation needed. Another example is a stack. A stack follows the last one first out. So the last one to be added is the first one to be removed. An example of a stack is, say if someone calls you and then tells you, show an example and implementation of stack in code. You define as you are define an empty list, right? Then you're now going to now use append and pop. So if you say stack does append and you append the value, let's say 2, right? If you print stack, you're going to see 2. Let's append another one. Let's say stack does append, and sure, why not? And if you print stack, you're going to see 2 and 3. 3 was the last one to be added. So based on this logic, if I remove the first one to go out is going to be 3. How do we now see this? We're now going to say stack dot pop. Remember in our last video I showed you all these things. So parentheses, don't forget, no, no. And now let's print stack. We're back to just having 2. So this is an example of a stack. If you carry a large portion of books and you're placing them one after each other on top of each other, You place your physics textbook, your biology textbook, your English textbook, your mathematics textbook. You now want to remove from that. Let's say you want to access another book. You are now going through the book. The first one you're going to remove, I've forgotten the order. I put everything in. You remove your mathematics textbook. So it's always the last one you put on top is the first one that is going to be removed. So that is the last in first. So that is the LIFO principle. Next, we have a queue which follows the opposite one. Q follows the FIFO, which is the first in, first out. So let's see a code representation of Q. Let's say first we're going to have to import something. So we import from collections. We're going to import the Q. Okay. Now we're going to define a variable. Let's call it Q. And we're going to equate it to the Q. Next, we want to now append a value to it. Almost similar to what we did before. Let's append to. Now let's print. Yeah, we have twins inside it now. Let's add another value. Let's say q the append 3. Let's print it again. Now using the FIFO principle, we are expecting that once we remove an element, the first one to come off is going to be number 2 because that was the first one we put in. To see this, I'm just going to say q dot top left and we print it. A perfect example of this is your normal day-to-day queues. Let's say we are lining up, we want to go and buy something like at the ShopRite checkout point. Everyone has formed the line. When the cashiers want to attend, they are not going to go to the back of the line and start attending to the last person who came. They are going to start from the first person to join the queue. That is a perfect example, a perfect way to analyze it. Like every coding is your day-to-day life. Don't stress yourself about it. Next, we have what is called a linked list. So this linked list is going to come up again later, but a linked list is a sequence of nodes, each containing data and a pointer to the next node. So you are going to have two stuffs or two sets of stuff stored in your list. The first one is going to be your node. It's going to be all the data referring to this current point of whatever it is you want to access now. Then second one is going to point you like to the next location. So not like a list where everything is just following each other in sequential order. You have one that's like plot A, the other one at plot Z. But even though the next one following plot A is at plot Z, you can still access it because if you are going through plot A, the next thing is not going to have a pointer. If you did C and C++, you should be familiar with what pointers are. It's going to have a pointer that will not tell you, okay, the next one following this one, you're going to have to go all the way to Z, but that is where part B of the book is at. And once you read Z, Z will direct you to wherever next is going to until you reach the final one, which is now going to direct you to a null. It's going to have a null pointer, so there's nothing after that. So instead of each element being beside each other, I have a note out before I cover everything. So there are two types. There is the single and double linked list. The single linked list are the ones that just point you to the next one, while the double ones point you to the next and previous. Like if you are watching a movie now, so okay, this is what you were watching before, or this is what you are going to watch next. Um, so now the implementation of this one is going to be a bit more complex. We're going to have to define our own append function ourselves. We're not going to use the predefined one, but it's okay. We are developers. That is what we do. So the first thing you want to do is actually define the node. So we're going to define a class. For those of you who don't know what a class is a blueprint to an object. For example, you can have a class person and it's going to now have, let's just be coding. So we're going to have a class called linked list. You don't need a parenthesis for this. But within this class, now we're going to have different functions. These functions are going to be the attributes and the methods. Attribute is going to be called using the init um I keep forgetting what decorator is that the word. It's just going to be defined using init, that is inid initialization. Basically, this goal is going to use to initialize the attributes relating to this. For example, if we're doing a pricing class, that is, you have the name, age, whatever, and ever, and ever, and ever. And after that, you now have other functions that define the methods, like this person can talk, this person can jump. I have videos where I dove deeper into class. But here now we're going to what we're going to be initializing is if I work in accelerate given double underscore the function. You have init, you have strings, you have this REPL. There are so many of them. So like if you want to put today video just talking about them, you can let me know. But we're going to have self, which helps us like personalize it to the initial object we're working with. Then next, we want to now collect the data, which is the data that is going to be stored. So for now, I'm not just going to have a default value, which is just going to be none. So we're now going to initialize it. We're going to say self.data is going to be equals to data. And now we're going to now initialize for the pointer. Because remember I said it holds two things. One is the data relating to this current node that you're on, and the next one is the pointer pointing to the next node. So we're going to say self.next is going to be equals to none. So that even if let's say there's no other one, if there's another one, we're going to override none. But if there isn't, we're just going to leave it node, which means you're not pointing anywhere else. Now we're going to now initialize another class. So this one is now going to be okay. This one, let's have this one as the current node. Then we're now going to define the linked list. This is going to be node. Then I have the linked list that will now access this node and make use of it. So we're going to say linked list. Almost the same thing. We're going to initialize it first. So this one is going to be self. We don't need to initialize the data again. And we're going to say self.head. So I can just keep track of what position we're currently on. It's going to be equals to node. We're not going to pass anything since it's just going to set data to none for now. And then we're now going to start defining the methods. So the first method we want, like in all the ones we did before, we made use of the append. So let's define our own append function because we cannot just use the predefined append function. Like all these things we use in Python, print, append, they are already functions that someone on their own can define, which you, if you wish to, you can do on your own. You can just give yourself as an example, just something I did, try and figure out how all these other functions function, basically. So we're going to define the append method, append. So we're going to take self, and we're going to take data. Next thing, we're now going to choose, okay, the new node is going to be equals to node, and we're just going to pass in whatever data it is that we're currently working on. But now that we've gotten the new, we need to know, okay, because when you're appending, you want to add something. So this new node is going to be the new value. Let's say we have two, four, now I want to add six. So six is what is going to be stored in new node. But to know where we're now going to place this, we now define what is our current position. So our current position is now going to be equals to self.head so that we can find, okay, where where are we currently? Because remember when we were defining the linked list, we initialized what our head was. Then next thing, you now need to find the node where the next. So here, here in the node function, we have something called next. By default is none. But if we have a next one, we're going to override none. So we'll now be looking through it. Okay, find the node where like the value is now none. So I think for the one that is none. If the value is none, that means there's nothing after it. So we'll now place it at the one after it. I hope I'm making sense. Basically, we're just looking for the last node. So we're going to say while the current dot next um is not equals to none, not equals to is the exclamation mark and equal sign. So while it's not equals to none, that means there's more after it. We're now going to change, okay, Since now we're at point one, point one dot next is not equal to none, move to point two. So we're just going to say core is equals to core dot next. And once we now finally finish flipping and have reached the point where the next answer that is now actually equals to none is where we now want to place our value. We're not going to say core dot next is equals to new underscore node. Do we understand? Now you can still on your own decide to do and add more features like defining the finding the length and what and so on and so forth. But yeah, next we have non-linear. So non-linear data structures. In this one, the elements are not arranged in a sequential manner. An example is graph. So now non-linear data structures are going to be a bit more confusing. So graph is a collection of nodes connected by edges. So that is like lines. I think I should have an image. I feel like I saved an image to explain it. Okay, here. So edges are these straight lines you are seeing. These are all the edges, and these circles here are the nodes. Ignore this adjacent list for now. We're going to revisit that. So to work with graphs more efficiently, you create a class to represent a graph as an adjacency. Is that how you pronounce it? Adjacent list in Python. So if you start checking out here, we have this point zero. What is point zero connected to? Check the edges. We have one going to one, we have one going to four. So here in our adjacency list, we're going to have one going to one and four. Same for number one, we have 0, 4, 3, 2. 0, 4, 3, 2. So it's just giving a more structured representation of the graph. Because if you want to start doing this graph in Python or your so now, how can we now actually represent it in Python? So now we're not trying to create this graph, we're trying to create this adjacency list representation in Python. So we're going to do this in a function. So the way we're going to do it, almost the same thing as what we just did now, define a class. Now, first things first, obviously, initialize it. So the other attributes we're going to be passing is the number of nodes we want to have. In that last one, I think we had 5. So we'll just ask, okay, what are the total amount of nodes you want? And next thing, for your edges also. So we're now going to just initialize. This part is the same old, same old. Now for this self.data, we are going to have a list of a list. So if we were representing this in Python, we'll have all these stuffs. Is there where okay, if I'm typing this now, it's just going to trace. We'll have all these stuff stored in one list. Then that list, if you were working with NumPy, you would call it, I think this should be a two-dimensional array. So you'd have your main list, and then you'd have the first one at index 0 is going to be let's just continue with our code. So what we're just trying to do is initialize a list that has multiple empty lists for every single element in the num node. So that is for underscore in range num underscore node. And let's see if this stuff is listening to me. Okay. Now we're now going to now start looping through it and now start fetching all the values to know where we're placing them. So we're just going to say for n1, which kind of like the index, and into the element in edges. So just initialize this ones also. And we're just going to do vice versa. Okay. Now, after this, now we just want to arrange how the work is going to be displayed. So if we run it now, it's just going to give us a long list because we initialize a list within a list. So, but now we want to structure it as an adjacency list the way it was in our um picture. So I'm just going to use under constructor REPR. Then we're just going to return. So this slash n is just for you to jump to a new line. What's happening? Okay. Then dot join it with the proper output that we're working with, which is going to have then we're just going to use string. String is just the main display function. It's kind of like this print statement for your function. Once we jump into Django, you're going to see more of it. Just going to return um self dot underscore repair. So now if we're now to implement this graph. Alright, so now we're going to now implement this and just test it with an object. So we're going to have our number of nodes, our edges. So like I was saying, the edges is just basically okay, we have 0. So remember in our graph, should we create the edges for this graph? Okay, let me just re-edit it for this graph because I'm stressing myself out. So we have 0, 0 is touching 4, 0 is touching 1. Let me just redo that quickly. So we said 0 is touching what? And let's clearly places there 1 and 4. So we have 0 touching 1. This 0 touching 1 is also going to represent 1 touching 0. And we have 0 touching 4, I think. That is also 4 touching 0. So we have 4 touching 0 already. We have 4 touching 1, 4 touching 3. So we'll just do 4 touching 1, 4 touching 3. Which other one do we have? Let me just clean this one. 3 touching 1. 3 touching 4. We already have that. 3 touching 4. 3 touching 1. Why am I tripping? 3 touching 1 and 3 touching 2. God, please help let it not be anyone I'm missing. 1 touching 4, 1 touching 3. 2 touching 1, 2 touching 3. 2 touching 1. 2 touching 3. Okay. 1, 2, 3, 4, 5, 6, 7. One, two, three, four, five, six, seven. Okay, perfect. Seven edges. If we don't know what I counted, I was counting the edge line here. So one, two, three, four, five, six, seven. So when we save this and run it, this should look like what we have here. So 0, 1, 4, 0, 4, 3, 2. It's not organized the same way, but just check it. 2, 1, 3. So you can have the logic to organize it from lowest to maximum. But we've created our own adjacency list. Come on. What else is on our agenda? We have trees. So a tree is a hierarchical structure with nodes connected by edges forming a tree-like shape. So we're done with this. So if we're to create a class for a tree, it's almost the same thing. So if you understood what we did before, we're just going to breeze trees. If you don't understand, go back to the last video. Create a class. This one is going to be our tree node. We're going to initialize it. We're going to collect the data. We're going to now initialize that data. And we're going to initialize an empty list for storing all the child nodes, because you know, like trees have branches and all the stuff. So we're going to have self dot children. I'm this scary because our square brace. Okay, then we're now going to create a function to add a new child, kind of like a method. So add underscore child. So it's going to be child underscore node. Then we're going to now append the self dot children dot append child underscore node. Yes. So this is going to add the child node to the list that we initialized in self dot children when we initialize the class. And then we're going to do our RPR also. So it's going to be def underscore repr underscore self. So now we're going to have levels. So there are going to be different levels and different branches. So we're going to start at 0, which is going to become like head when we're working with um linked list. So we're going to have level is equals to 0. Then we're going to the value we want to return. Okay, now you want to implement this. We're now going to create the root node. So we're going to say root is going to be equals to tree node, and that should be our data. Then we're now going to create some child nodes, that is like the branches under it. We're going to have, let me just, okay, I'll just copy it and we'll just copy and paste. Child one is going to be equals to tree node. I'll just copy this. Okay, now we're going to add these children to the root. So we're going to say root dot add child, child one. We're going to repeat root dot add child, child two. And then if you want to now create a sub branch of a branch or whatever you call it, so let's just add root three to one of the child. So child one dot add child, child three. Okay, then now we can print roots. A zero. Alright, is this where the error is from? Yes. So let's just fix that. It's add underscore child. Alright, so if we run this now, we're going to have our tree. So we have our root class. On that root, we have child one and child two. On that child one, we have child three, and you can keep on going and branching it. Or just think of it as you have your directory here. You have Python. Under Python, you have, okay, I don't have enough folders. So let's do another one. We have extended libraries. Under extended libraries, we have Python. Under Python, we have so many other directories, all of which have their own branches and branches and branches. So yeah, next let's just a quick differentiation between linear and non-linear DS. Apart from the obvious where elements are stored in a linear sequence for linear data structure, and for non-linear they are stored hierarchically. That is like you're inheriting from this, kind of like the trees which we just did. Examples of linear data structures are arrays, stacks, queues, linked lists, all of which we covered. An example of nonlinear are graph and trees. In linear data structure, it's easier to implement and access sequentially, while in nonlinear, it's more complex. It's a more complex relationship and connection. So why do people learn about data structures? Why is everyone always talking about data structure and algorithm? It's an efficient problem solving tool. It implements optimized solutions. It aids in competitive programming, and it's the foundation for a lot of advanced topics, some of which we're going to come across shortly. Now, just reverting back to the beginning, was the difference between algorithm versus a code. An algorithm is a logical sequence of steps to solve a problem, which we already know. A code is a specific implementation of an algorithm in a preferred language, in this case, Python. And the relationship between both of them, code translates the logic of an algorithm in an executive form. Like when I was explaining algorithm, I was saying I'm saying this algorithm to you in English, which is your pseudocode, and any programmer can now take this pseudocode and try to now turn it into a programming language, whether it's C++, Java, C Sharp, Python, Ruby, Swift, Dart, whatever their heart desires. So now we're just going to brief through this. I'm not going to touch on this video because it's a bit bulky. If you want me to do the whole video on that, you can let me know. As English is not my language. Asymptotic notation. It's a mathematical tool used to describe the limiting behavior of a function. It helps to analyze the efficiency of an algorithm, and there are three main types, which is the big O notation that everybody did in secondary school. There's the omega notation, which I feel like every computer science or every engineering student should have come across at least in 100 level, and there's the theta notation. Big O notation is the most popular. It's a way to describe how well an algorithm performs as its input size grows. So if you're like, you can have a small you can have a small like input you're working with and everything is working fine, but what's going to happen when you start adding more and more and more and more and more? That is what I'm going to leave you guys on. If you want me to talk further on that, you can let me know. And I'm just going to briefly brief you on some algorithms. I'm just going to touch on one. There are 1,000 different algorithms. That's an exaggeration, obviously. But if you want to do different algorithms, especially for the sorting algorithms, let me do some of the sorting algorithms include bubble sort, selection sort, insertion sort, merge sort, quick sort, heap sort, and so on and so forth. There are so many other types of sorting algorithms. But let's just touch on the bubble sort quickly because we're going to reference it in some future videos. Bubble sort compares two adjacent elements and swaps until they are in the internet order. So let's take, for example, we have a sequence of numbers one. Let me disorganize it. Ooh, I'm not good at disorganizing things, right? So if I'm not creating a sort for this, we'll now take one. Is one greater than four? No, let me just copy and paste because I promise I'm not going to be typing this over and over and over again. So is one greater than four? No. So your sequence is going to stay. You now say, okay, is four greater than six? No. Okay, is six greater than three? Yes. So now what you're now going to do is you're now going to take six and swap it with three. You're now going to say, okay, copy and paste again. Gosh, I'm so lazy. You're now going to say, okay, is six greater than nine? No. Is nine greater than two? Yes. You're now going to say, okay, swap two and nine. You're not going to now start this whole process again until two reaches in between one and four and three moves, you get. So it's just comparing once the one you're working with now. So now you're not going to start, okay, is one greater than four? No, is four greater than three? Yes, move four. Is you get, you just be going like that, like that, like that. It's a long process. There are so many other algorithms that are way better. Let's do this quickly in Python, and then if there's any other algorithm you want me to explain the implementation in Python, let me know. Define a function called bubble underscore sort. This is how you spell bubble. Bubble underscore sort. And we're just going to have the array that we're going to be working with. Yeah, we're not using self because this is not a class. We don't need to initialize anything. So now we're going to say get the length of how long the array is. So we're going to know how many elements we need to loop through. So we're going to len array. Then we're going to say for every element in that array, that's for I in the length of the array, we're now going to say like, okay, mark that this element we're currently working with has been swapped. So we're going to say swapped is equals to false by default. So once it's been swapped, we're not going to, okay, true. Then we're now going to do a second loop. So we're going to say for j in the element less than the current element we're on. So for j in range 0, n minus I, because we want the one lesser than what we are at, minus 1. We're now going to check if the array of the current elements we're now on, which is our j, is greater than, right, so where was I? Sorry, I had a call. So I'm saying if the current position where we are at right now is greater than the one following it, so that is going to be j plus 1. Then we're now going to say switch the position. So in Python, if you want to switch two positions, let's say you have I and j and you want to switch I to be in J and J to be in I. You're going to say I and J is equals to J and is equals to JI with a comma. So we're going to have array J and array I plus J plus 1. And we're going to say is going to be equals to, we're just going to do the same thing but switch it. So, okay, they almost did it first. Let's just switch. I'm a lazy person, I know. So J plus 1, J plus 1, J. Yeah. And then we're going to set swapped equals to true. Then if not swapped, we'll just end it. To end the loop, you use break. Okay. So this is always not going to be diving deeper into different types of algorithms. Like I said, if you want me to do a video on that, let me know in the comment section below. In the next video, we're going to be focusing on things like models. What else are we going to touch in next video? Let me just see. I have like a list of everything I need to cover. So let me just quickly brief through everything that is going to be present in the next video so we know. We're going to do models, we're going to do lambda functions, which I think I mentioned it in the last video, functions within a line. They're not like your normal def functions. We're going to do decorators, which are some of the things we've been touching since. We're going to do iterators and regex, that is regular expression. But yeah, without further ado, have a beautiful rest of your day. If you have any question, let me know in the comment section below. Like, share, subscribe, and I'll see you guys in the next video. Bye guys.